Fracture toughness is an essential characteristic of a structural material, indicating the resistance of a material to cracks and governed by the work needed to destroy a biomaterial, also called work of fracture. The fracture toughness is measured by the critical stress intensity factor, Kc, and critical strain energy release rate, G. The fracture toughness properties of materials vary over a wide range, about 5 orders of magnitude. High fracture toughness in metals is generally achieved by increasing the ductility, but this often comes at the expense of lower yield strength. The fracture toughness of metals and other ductile materials depends on their thickness. The toughness is highest when plane stress conditions exist at the crack tip. This occurs when the material is thin, typically less than several millimeters. The fracture toughness of metals can be improved without significant loss in strength in several ways, including minimizing the impurity content, reducing the grain size, and reducing the amount and size of intermetallic particles at the grain boundaries. The fracture toughness properties of fiber polymer composites are anisotropic. In this case, the highest fracture resistance occurred with an in-plane fracture involving breakage and pullout of the fibers. Conversely, the lowest fracture resistance occurs by interlaminar cracking. In addition, the fracture toughness properties of wood and metals with a directional grain structure are also anisotropic. The fracture toughness of fiber polymer composites can be improved by using toughening resins, thermoplastic interleaving, through thickness reinforcement by stitching, pinning, or orthogonal weaving, as well as other processes. As we mentioned, there are 2 types of fractures: ductile and brittle. In this case, the brittle fracture occurs through the crack propagation mechanism. In the 1920s, Griffith postulated that most materials contain inherent flaws in the form of microscopic voids or cracks. These flaws serve as points of stress concentration or as stress risers. Consequently, the applied stress is magnified at the tips of these flaws, and the degree of stress amplification increases as the radius of the tip of the flaw decreases. Thus, the sharper the crack, the higher will be the stress. As a crack propagates during fracture, it has a sharp tip which causes a stress concentration and high stress ahead of the crack. In the case of a ductile material, this stress causes plastic deformation of the material at the tip, thus blunting the crack and reducing the stress. However, since a brittle material does not exhibit plastic deformation, its crack tip remains sharp, causing high stresses and rapid failure. Brittle materials are usually stronger under compressive loading than other loading modes because the crack tips are compressed, decreasing the crack propagation rate. Regarding the toughness measurements, it is essential to note that the toughness of brittle materials depends on the test technique employed. These techniques are classified into long crack and short crack methods. Long crack methods consist of single-edge notched beam, SANB, and single-edge V-notched beam, SVNB techniques. In general, the stress distribution near a flaw can be described in terms of the stress intensity factor, K. This factor helps to determine the stress at any point situated at a distance, r, and at an angle, 0, from the crack tip. In the following equation, we can see the relationship between stress, the crack length, and y related to the specimen's geometry. Particularly, in the single-edge notched beam, the evaluation of mode I critical stress intensity factor, KIC, is based on the following classical expression. In this expression, Y is equal to the following equation: P is fracture load, H is the specimen thickness, D is the specimen width, C is the crack length, and L is the span length. On the other hand, the single-edge V-notched beam technique is a modified version of the SENB technique. A sharp V-notch is produced by polishing the notch root with a razor blade coated with diamond paste. The notch radius can be made smaller than 10 micrometers by polishing. The samples are fractured using a 4-point bending setup on a universal testing machine. Then the fracture load is recorded, and fracture toughness can be calculated from the following equation. PF, low, Li, B, and W are fracture load, outer span, inner span, specimen width, and specimen depth, respectively. Alpha is equal to the pre-crack size and F alpha. Finally, another important test to carry out is the fatigue test. Since the fatigue test results are an essential basis for assessing life expectancy and strength of materials, as well as components or structures under cyclic load. Fatigue failure has several stages. The first stage of fatigue-induced failure is crack initiation. Cracks usually initiate either at existing sites of stress concentration or as the result of an increase in the number of dislocations with the crystal structure of the material, which leads to imperfections and crack formation. The cyclic nature of the stress causes the crack growth to occur intermittently, with propagation occurring every time the material is loaded. The third stage is the final fracture, which occurs when the crack grows to a critical size and the critical stress intensity factor is reached. Thus, fatigue life is defined as the number of loading or stress cycles of a specified character that a specimen sustains before failure of a specified nature occurs. As you can see in the following figure, the fatigue properties of a material are graphed as a stress number of cycles to failure. Historically, SN curve has been expressed in the form of an exponential relationship between applied stress sigma and number of cycles to failure NF. In most materials, there is a minimum stress level below which fatigue failure does not occur irrespective of the number of loading cycles. This stress level is known as the endurance limit, and the SN plot becomes horizontal at this point. The number of cycles is related to engine speed. Therefore, it can be converted to equivalent durability hours. Fatigue life is affected by cyclic stresses, residual stresses, material properties, internal defects, grain size, temperature, design geometry, surface quality, oxidation, corrosion, etc. As we see in this lecture, as biomaterials are fashioned into useful devices or implants, it is important that during the design process, their behavior under operating conditions is carefully predicted and deemed to be safe and efficacious. By using a standard test to measure biomaterial properties, one can predict how the material will behave to a large degree, thus minimizing the risk of failure in use. This is the basis of all engineering design and is essential.